everyone, welcome to the live stream. This is episode 138. It's our 39th episode, and we'll be interviewing Adam Taylor. We're super excited about this interview. So Adam Taylor is the founder of Aduvio Engineering. Pronounce it how you like. It is created to support engineers and developers with application-specific complex FPGA and SoC design. So let's find out what that really means from Adam Taylor himself. So switching over so we can hear from Adam Taylor. Hey, what's up, Adam?
Hey, how you doing?
How you doing?
I'm doing really well. Yeah,
Awesome.
really well.
Super excited to have you. And like just,
I'm excited to be here.
yeah, we want to learn all we can in, like in as much, as quickly as possible.
Yeah.
Well, you have half an hour, so I can teach you everything I know in the next 10 minutes. So we'll be good.
Perfect. And then 20 minutes for Q&A.
Exactly. Yeah.
All right, so I guess we'll get started. Like, how does somebody get into application-specific, complex FPGA and SoC design? Like, what got you started?
That's a good question. So, I mean, I started years ago. So I've been designing FPGAs for nearly 20 years now. Started out, actually, back when I was a graduate. When I was a graduate engineer, started designing signal processing FPGAs for Raytheon, and then throughout my career, I've been quite lucky to design FPGAs for a range of things, from submarines to nuclear reactors to satellites to power supplies to a range of really cool applications, really. They just sort of maybe 4 or 5 years ago now, I decided that I'd gone high up enough the management tree, and I actually wanted to just do my first love, which was engineering. So I formed my business, and here we are now talking.
Nice.
Wow. So when you got into like FPGAs, what made you want to kind of share your like findings and knowledge with the world and like become more of a mentor and consultant?
So I've always enjoyed kind of sharing what I knew about FPGAs. And there's another reason as well, actually, and I write things down because I'm quite forgetful. So it's quite useful to actually have fairly detailed notes saying sort of, this is how I did this. And it just became sort of natural to share that. So I mean, I think it's now 9 years since I wrote my first paper for Xilinx on how to design safety critical state machines, and we're now just about 2 weeks shy of 6 years for the blog. So I've done a weekly blog on FPGA design for 6 years, and it seems to be quite well received. People keep reading it either out of sympathy or out of interest. So. So it does go quite well, and it's good fun to actually share knowledge as well, and I find it a really good way to learn new skills as well and keep myself sort of sharp. Because obviously when you're working for a client or you're working for a company, you've got a very specific job in mind, that focuses you on doing that job. But actually when you do it as a blogger, when you create a project for Hackster or something, you can actually create something that makes your heart sing, that's interesting to you. And then you can go away and create that and learn a little bit about new skills and such like as you go through it.
Yeah, that's great. So you were talking about state machines. That's very theoretical. Like I remember learning that in like a digital logic design class that I took. And like, how do you connect such theoretical concepts to like implementation on like like in an practical way?
So I mean, state machines are an interesting section of digital design and of FPGA design, because they're really pretty much one of the hearts of everything that we do in our design. You want things to move through sequentially. You want to be able to move through various states and do things. So if you want a really simple example, is if you want to have a RS-232 interface, these days you're going to use a USB to RS-232, but you're still going to have RS-232 in there, and you're going to have a shift register and such like to actually receive the words. But then you're going to have a state machine that actually says, well, what have I received and how do I go away and do it, and what do I do with this data? And they're really quite. They are a little theoretical. You do learn about them at university, and then obviously they'll teach you how to use them, how to write them in FPGAs. Generally, they'll teach you how to do it the wrong way. I've yet to find a university that teaches the right way for state machine design in FPGAs, because they're very theoretical. Mm-hmm. So they'll teach you the two-process method, where you have a clock process and then a combinatorial process. In reality, you're just going to have one process, which is a clock process, and it makes it much easier to debug, much less risky, and you end up with many fewer glitches and such like on your output, and everything's nicely registered as well. But yeah, I mean, I use them all over the place. So one of my core jobs is I do a lot of work in space. So I do a lot of design for the European Space Agency and so on. And I've just been designing I probably can't tell you who the client is or what the mission is, but I've just been I actually designed the PCB for this with a partner as well, and we've done three FPGAs, and as part of one of those, I had to design the other week. I had to design a 78 state machine.
Whoa!
To actually control and sequence what was going off when. In most applications, you just say, hey, this is a little bit complicated. I'll put a microblaze or an ARM core in something and do it in software. But unfortunately, if you're doing mission critical things for like space, then it's much easier to verify a state machine than it is to verify processes and such like, and the behavior than if you get single event effects. So yeah, we end up with like a 78 state machine, and then of course you have to make it a power of 2. You have to address all the unmapped states for things like bit flips in orbit, such if it goes into an illegal state, it can lock up. So once you've actually implemented all the states that you want, you then have to go away and address all the unused states, and it's a power of 2, so it's going to be 128 states that you have to actually write at the end of it all and manipulate it through. So they're quite a theoretical thing, but if you can design a state machine, then you can pretty much do anything. Although at university they always teach you the weird thing like pattern detection and such like, or traffic lights. They'd be much better saying here's how to do like an RS-232 interface to receive some commands and turn on some LEDs or read some switch values back or something, because that's more what you're likely to use it for in real life.
Wow. So just a little thing on the topic of space. What would you say is the difference between designing a board for use here on the ground versus up in space?
Well, so I have funny you should mention that, I have a 3-day course that you can attend if you like on how to design FPGAs and boards for that. Not that that's a plug at all. It's actually quite interesting because you do a lot more design analysis essentially, because you're considering the absolute worst case effects, because nobody's going to be able to touch it for maybe, if it's sort of like a scientific mission, sort of 7 years or so. If it's a telecoms mission or something a little bit more special than that, it's going to be sort of 15, 20 years. So you've got to be really sure that your design is going to work for that period of time. So you're going to do a lot of design. So if you're designing a board, for instance, not only are you going to design the architecture, but you're going to consider redundancy paths if you've got any redundancy. You're going to consider single points of failure. You're going to consider the worst case analysis. So when you do the worst case analysis, you're going to take into account really everything, sort of, the drift of components with temperature, with tolerance, try and work out what the worst case corner conditions are across that, and then take into account aging and radiation effects, and then prove that it's still going to meet that condition. So there's a lot more design analysis that comes in. And honestly, when you're designing things for space, actually, you're designing things with slightly older components as well, because you want them to sort of specific quality levels and such like, which can be a little bit trickier and harder to get. And heritage is quite a big thing in space as well. So if you've designed something, if the power supply is flowing on one or FPGA is flowing on one, then people tend to say, oh, that worked okay, so you can fly that again.
Yeah. If it isn't broke, don't fix it.
Yeah, if it hasn't broke. But it's really quite exciting. It's really quite a cool and exciting area to work in.
Yeah, I mean, that's amazing.
Yeah, very cool. Do you have like software available to do all this analysis for all these various conditions, or do you just use math equations? Well,
like all engineers, I'm absolutely terrible at math, so we use software.
Yeah.
So we obviously you use a lot of FPGAs are quite simple really, because you're looking at time enclosure, so you're trying to prove that you can get time enclosure. You're putting a little bit of derating in there. You're looking at failure mode effects in the FPGA. What happens if this pin gets stuck high, gets stuck low? So it's fairly quite similar. If you're doing sort of analog electronics, then you can do it with simulation. You can do it with SPICE simulation tools and such like, and then reliability calculations. There are software tools out there that will help you put all your stuff in. But a lot of times you just come back to using Excel spreadsheets and reference manuals to work it all out. So sometimes it's just quicker and easier.
Okay, makes sense. Yeah.
Yeah.
Okay, so you want to go this one?
Yeah.
Or?
So we've spoken a lot about like complex FPGA stuff, and you know that can be super intimidating for somebody who's like just hearing this conversation and maybe like going like, oh, I was interested in FPGAs, but now it sounds too hard. So how
used
would
in
you?
space.
Yeah, exactly. So how would you recommend like somebody who just wants to get started out, like, but is super interested? Maybe their ultimate goal is to make like an SoC softcore on an FPGA or something. Like, how can they get started? Get their hands like into it.
So I mean, FPGAs have got this. Well, they have this, what shall we say, reputation for having a pretty much vertical learning curve to get involved with and get anything out of it. And to be honest, I don't think that's the case anymore. Oh, excuse me. I woke up this morning with a terrible sore throat. So it's quite easy to get through it's quite easy these days to get hold of the software environments that you can use. So, you can get Bravado, you can get Quartus and so on. For actually experimenting and creating on, and I'm a real big fan, as you guess from the sort of nigh on sort of 300-ish blogs I've written on the Zing. I'm a real big fan of the Zing. Excuse me, because that software-hardware partition, it really allows you to begin to bring something up on the software side if you're familiar with software. So you can write some C, you can see how that works. You can have a slow introduction to the tool and doing some configuration in Bravado for changing slight configurations on the Zing side, on the processing side of things, and then you can progress to sort of putting in some IP cores and such like, or maybe writing your own sort of VHDL or Verilog, and then gradually building it through. And there's a lot of resources out there on the web these days that they're designed to help people get going and get started with creating FPGA-based design. So they're not as difficult. When I first started 20 years ago, it was really difficult to get hold of the tools, to get hold of simulators. Unless you did it for a company who could afford the license fees, it was really quite difficult. But these days, it's actually not. They're fairly accessible. All you need to is just a little bit of time. And there's a lot of communities as well. There's a lot of FPGA-based communities. There's the Xilinx forum. There's a Reddit FPGA subreddit or whatever it's called. And there's a lot of people out there that will actually help you. If you try to help yourself as opposed to say, hey, how do I do this? I'm trying to do this, and this is where I got stuck, and this is what I think I'm doing. Then there's a lot of people that will, myself included. I get a lot of emails from people all the time saying, hey, how do I do this? Nice. And generally I try and email them back. Sometimes I get a little bit. I think I'll reply to that, and then a week later they email me and say, hey, did you see this? It's yes, I did. Sorry about that.
Yeah.
But yeah, there's a lot of people out there that will help you get going with FPGAs as well.
All right, that's good to know. So, like, what are so say somebody starts with a Xilinx FPGA. Would you recommend starting with like one that has the drag and drop, like where you can do the IP blocks and things like that?
Yeah, so really, if you're gonna start with a Xilinx FPGA, get a 7 series and up FPGA. So I'm a big fan. I've got a lot of development boards. So I'm a big fan of the Pink board. The Pink that allows you to use Python with the Xilinx. I'm a real big fan of Pink. I think that's really great. I think that opens the door to a lot of new users as well, and it eases the use in there. And if people want to know a little bit more about Pink, obviously I've done a few specific blogs on my blog over the years doing an introduction to it. But also there's other boards, the Arty series of boards, the Arty boards and the Microzet boards and the Ultra 96. They're really good boards to sort of get started with. If you use Bravado, you can use the Xilinx IP integrator, and it's really quite possible that you never have to write a line of VHDL. You might find yourself writing a lot of software to configure those IP blocks that are connected in there,
right.
Either in a Linux format or in a bare metal format, but actually it's really possible this day and age to go through and create some pretty complex applications without actually writing a line of VHDL or Verilog. So if you wanted to do image processing, for instance, there's all the blocks provided that you can literally just drop in and then configure over software to get a full image input to image output. And of course, you can use people can use high-level synthesis as well. So if they're familiar with C, you can write C and then actually get that to compile using high-level synthesis down to VHDL or Verilog that you can then drop into your design. So again, it opens it up opens up the ecosystem a little bit more for people to use.
Right. Yeah, that makes sense.
So, what would you say then is the next frontier in FPGA development and just embedded system development in general?
So I think it's quite interesting. I think you're seeing a sort of a merging of platforms and an increasing level of abstraction. So if you think about sort of programmable, and I'll say programmable logic, not FPGA. If you think about programmable logic when it first came out in sort of the 70s, I guess, people were doing it with logic equations like you got taught at university. They're actually doing Carnot maps and such like, and programming into little 22v10s, into PALs and such like, and then moving it, and then putting those in their design. And once they get quite large, you can't do that. So the next level of abstraction came in that you wanted to be able to draw them schematically with AND and OR gates and D-type flip-flops and such like, and then the devices get so big that you can't do that, and then that VHDL and Verilog come into play. And now these devices are so big, and they're really moving from being just an FPGA or programmable logic to being sort of basically a compute platform. Where if you take a look at the Zinc, you've got the A9 cores, you've got the programmable logic. If you take a look at the bigger brother, the MPSoC and even the RFSOC, you've got real true heterogeneous systems on chip where you've got high performance processors, GPUs, and with the RFSoC, you've even got multi-gigasample ADCs and DACs. And then if you look at the next step, that comes with the Versal range of devices, they're just amazing. And it's quite interesting, but we kind of have to keep moving on this. And for me, it's quite important because you kind of have to keep moving on this increasing levels of abstraction and working at a higher and higher level to actually be able to properly use these tools. You're using system optimizing compilers and such like to actually be able to create your application once and then sort of partition it from this, say, well, I want this in the processor side, this in the programmable logic side. And I think that's pretty much where it's really going. I'm not sure of VHDL, just for the people that are going to shout at me for saying this, that it's moving up to HLS and beyond. I'm not sure VHDL and Verilog are going to go away entirely because high level stuff's really great for signal processing, data processing, AI, and MI type stuff. But it's not so good for if you want to design an interface, say, for a specific object interface. So I think VHDL and Verilog IP blocks will be around for a long time, but I think they'll just get pulled in as libraries into the higher level software as well when it's doing its running and compilation. So I think that's where the next challenge is. I think is how to effectively and efficiently use all these resources that are now available. Because obviously you could do it all in VHDL or Verilog, you could do it all at the gate level, but the management aren't going to like it when you say it's going to take 5 years to do this. Whereas what we really want as engineers is to get our things out the door on time, on quality, and on budget. So we have to move up that level of abstraction.
Yeah, and having that higher level of abstraction opens it up for the masses, like more and more people to use it.
It does. It does. It really opens it up to sort of the traditional world of software engineers. And I do a lot of training, obviously, and a lot of teaching people. And I've seen a few software engineers just doing purely sort of C, C++ based high level synthesis designs into traditional FPGAs. And they've read the manuals, and it's they've got it working, and they've got it doing what they wanted. They just wanted me to come and talk to them to sort of help them finesse around the edge, make it a little bit more efficient and a little bit more higher performing. But what they've done was pretty good. So I think you're going to see more and more of that. And obviously, there's a lot more software engineers in the world than there are FPGA engineers as well. So it's a marketing thing at the end of the day as well. You want to be able to sell as many devices as possible.
True. Yeah, I think it's also an important point that abstractions have to get more efficient in the translation of higher level languages to the machine state machine level in the FPGA, because the more you abstract, the more bulk you end up having in general, right?
It is, yeah, you do, but yeah, you have to look at kind of is good enough good enough?
Right.
And better is the enemy of engineering. I've worked with a lot of engineering companies, and they're like, we could get it slightly better, the performance slightly better, and if we spent another week on it or another 2 weeks on it, it's like, well, what's the requirement? Does it meet the requirement or not? If it meets the requirement, then stop worrying about it and ship it. If it doesn't, then do something about it to try and improve it. And I think that's the case where you get with this high level stuff. I mean, at the moment, HLS is probably not as efficient as writing something by hand in VHDL or Verilog, right. But it's a lot faster, and if that faster design flow gives you a solution that meets your requirements, then it's good enough, and get it out the door.
True.
And it's like the compiler wars as well, when they were assembler versus C and such like in compilers, and people say, well, you can't compile as well as I can write my assembler, and that's the same for VHDL or Verilog at this point in time. But now you'd be hard pushed to find somebody that can write assembler much more efficient than what the compilers can pop out of them.
Right.
So again, it's just time and abstraction and such like. It's a journey, and for most things, if it's good enough, get it done and get it out the door and build your customer for it.
All right, yeah, that makes sense.
So, do you know of any upcoming trainings or events, or just things that the community could leverage in order to, get more familiar with FPGAs, get more skills in them?
So I mean, obviously there's Xilinx developer forums coming up, and they've got sessions in the US. So I'll be in San Jose next week for the Xilinx developer one. There's one in Europe, I think it's in The Hague this year, and there's one in Asia. I think it's in China. So they're good for learning that. There's excuse me. There's a lot of good conferences about as well that cover it. But there's a lot of good. Honestly, the best place to start looking is sort of material online. Taking a look at some of the blogs that people produce, some of the elements like the courses on Element 14 that are there under the Essentials, banner and such like on Element 14. There's a lot of good introductory courses there. I say that because I wrote them. But yeah, there's a lot of good stuff floating about, and a lot of material.
Yeah.
Okay, just Google Adam Taylor.
Yeah, you'll find so many blogs. I mean, you made a book out of your MicroZ Chronicles, right? Or there is a book?
I made 3 books out of them. Yeah.
Nice.
Wow.
Yeah.
And then I stopped. That was the end of the 3rd year, and then I stopped compiling them all together just because I didn't have any time. So we're now at the end of the 6th year. So
3 more books.
So yeah. Maybe I'll have to set my one employee a task this year to collate them all together when I do our annual appraisal.
Yeah. Wow.
Yeah, no, that's really cool. I mean, I was looking at one of your Hackster blogs, and just things like, how to implement I2C or SPI on an FPGA, things like that are always you always want communication protocols for when you're adding sensors or things like that. So it's important stuff. So.
Mm-hmm.
You do, and it is. And I2C is the protocol that I hate the most. Whenever you think it's going to be nice and easy to get up and work in here, and somebody says it's an I2C bus, well, there goes my week then. Yeah, it's very useful for it. Obviously, you want to have these things, and hopefully people read them and reference. So I mean, the blogs. To be fair, the blogs have been phenomenally successful. They've had about 20 million views or something over the years, and
wow.
We've just did about 100,000 views, I think, on Hackster. So it's pretty good. It's exciting times to be working with FPGAs.
Right. Yeah, it's really good to hear that you get emails from people, you're helping them out. It does seem like there's engagement in the FPGA community, because sometimes it seems that FPGAs have much less in terms of community compared to any other software based or the Raspberry Pi or just other software communities. Yeah. But I guess there are resources out there if you just look a little bit.
I think there are, and that's it. Yeah, you have to look a little bit, and I think FPGAs are a little bit more specialist as well, because most people kind of run into them at university if they're doing an engineering degree or a computer science degree. Maybe if you're kind of like a hobbyist and you bought a Raspberry Pi or you bought some Arduinos, you might not be too familiar that the FPGAs exist, and then you might read scare stories and think, well, they're just for professionals. Well, they're really not. They're quite accessible and easy to use. If I can do it, anyone can do it. Honestly, that's the thing I tell everybody. If I can do it, anyone can do it.
Nice. Awesome.
Okay. Well, so is there anything else you'd like to share with our viewers? Any words of advice, for hardware makers, enthusiasts?
I don't know. Words of advice. just keep on trying, I guess, is the main. That's the thing, when you want to quit, or when you look at it and think, hey, why did I start doing this? I should have done something different. Just keep on working at it and looking at it, and take a little time, go for a walk, go make a cup of tea or something, and you never know. Sometimes inspiration pops into your mind as to why you're facing the issues that you are. But overall, to be fair, there is really nothing better in the world than seeing something working. No, where you've sweat and struggled at it and thought about it, and you've lost sleep about it, and even you've dreamed about it. I find myself dreaming about it all the time, and you sit there like, and then finally one day, you get through this thing where you're knocking down errors one after the other, and you think, oh, this is never going to work. But then finally it does, and there is really nothing better than that feeling. So I spend a lot of time working from my home office, which is a bit of you can't see it too well, but it's a bit of a mess. But I share it obviously with my wife and kid. And there is sometimes, they can tell when I get things working because I start shouting and screaming and dancing around the office. Even after all these years of doing stuff, you kind of still like, yeah, it's really good. It works. There's nothing better. There's nothing better than this, really. It's like we're quite blessed, really, that we get to get up and do something that generally we enjoy.
Yeah, that makes a lot of sense. And people like you and other members who work on this stuff and put their work online, it's really inspirational, I feel like, for people who are getting into it, because it's not only you don't feel alone in it. There's a support system out there, even if you're not directly interacting. So that's also really nice.
Yeah.
Awesome.
Yeah, I think it works quite well. I think there's a lot of people out there creating good content out there.
Yeah.
Great. Well, I don't think if anybody watching the stream has any questions, feel free to put it in the chat now. We'll wait a minute just for the stream to catch up for that.
Yeah.
But yeah, besides that, it's been great talking. I got very surprised when you said that you were working on things for the European Space Agency. That's amazing.
It's pretty cool. It is. Well, it's just undergoing testing at the moment, so it's pretty cool if it works. If it doesn't, it's going to be like, oh no, how are we going to get this to work? But no, I think generally it's quite exciting, really.
Right.
So is this your first time working with them, or have you done things before?
I've got a long. So for like 7 years, I was one of the sort of lead engineers, responsible engineers at Astrium Satellites, designing FPGAs and boards for telecommunications satellites. Then I was the chief engineer for a few years at E2V, doing image processing for satellites and such like as well. So it was really I've got quite a history in the sort of space area and sort of high reliability, how to design sort of mission critical sort of systems.
Yes. So you already have your designs out in space, circumventing the globe.
I do, yeah. I on one of them. So we did a little one. We did it in our lunchtime. We did a thing called UQ, which I did in the lunch, which I did through my lunchtime when I was at Astrium, or Airbus now as it is. And actually, we never knew, but when they launched that, they'd machined everybody's name onto the metalwork of the thing. So my name's zipping around well, maybe it's burnt up now, but my name was zipping around in space for a while. So it was
so cool.
It was pretty cool, and I've got a photo of that somewhere. So.
Wow, cool. That's amazing. Just out of curiosity, so how much would you say, roughly? I know this is hard to estimate, ratio-wise. Self-learning to what you learned in courses or school for this kind of FPGA or embedded systems knowledge?
That's a tricky question. So I think I got a good grounding when I was at university. So I went to a reasonably good university that sort of taught us FPGA design. Well, at least when I graduated, I thought I knew FPGA design anyway. So you turn up at your first company and hey, we've got FPGAs, and I'm like, I know how to design those. And then you suddenly realise that actually you know nothing, and that's when you first start learning. But I've been really lucky, to be fair. I've worked on a lot of projects and such. But a lot of it's come from some, from the university, from some courses that I've been on over the years. Sort of VHDL design and Tickle design courses and such like. But mostly these days it's kind of just self-learning,
right?
And just reading user guides, manuals, and and working it out.
Yeah. I think like one of the things like I personally as somebody who's trying to learn struggle with is like how much do I just read the theory or like how it works and then how much time do I spend doing that before getting into it, you know what I mean? Because if I get into it too early, I don't know what I'm doing, but maybe they go hand in hand, I don't know.
I think you need to understand a bit of the theory up front, like the stages of FPGA design, how it goes through. Otherwise, you're going to be a little bit lost when you're trying to do it. So you need to know kind of like you create your RTL, you do your simulation and verification, you do synthesis, and then you do placement, and then you do routing. And it's quite important to understand each one of those elements and what the input to each input element is and what the output from that process is as well, and how it works, so as you can create your design effectively.
Right, that makes sense. Okay.
Cool. Well, I don't think we have any questions, so with that, thank you, Adam, for coming on the stream.
Thank you very much. I shall get back to my slow lingering mantling death now.
Oh gosh.
All right. Well, it was great talking to you, and we hope to see you again at some point soon, hopefully.
You will, and hopefully you'll be seeing some. I've got a couple of your creator boards as well, so hopefully you'll be seeing some projects popping up on those as well.
Great. So exciting!
Awesome. Looking forward to it.
Projects we can follow.
Yeah.
Well, probably you could tell me you got it completely wrong.
All right. Well, thank you, Adam. We'll speak soon.
Yeah. Bye.
You will. Thank you very much. Bye.
Bye. Let's see. How do I do this?
Yeah.
Sorry.
No,
I messed that up. Okay. All right. Still working out the kinks.
Yeah. You have a new setup here.
Cool.
Okay. Oh, now we're full screen there.
Haha. Hello. All right.
Okay.
Here. This is what I want.
Stay with us for a second here.
Yes. 1 second.
Ooh, can you just select the scene at the bottom?
Huh?
Can you just select the scene at the bottom?
I guess I can, yeah. But we won't be able to see it.
Yeah, that's fine.
But that's okay.
It's front
Banner. We'll just do the banner.
Yeah,
hello, everyone.
Cool. Hi. Yeah,
sorry, that took a bit.
Cool.
So, yeah. All right. Cool.
That was fun. That was a lot. I kind of want to rewatch it so that I reabsorb everything he said.
Yeah, no, it does. Yeah, that was very interesting.
Mm-hmm.
Yeah.
Awesome. Cool. So, I guess announcements now. So we have the Matrix Labs with Snips and ARM contests on Hackster going on right now. We're like halfway in at this point?
Yeah, there's a month left. October 27th is the deadline for submissions. If you have a Matrix voice or creator or want to get one and get started, you should go now. A month is pretty good, so you still have time.
Mm-hmm. Yep.
Yeah.
And then other things.
We'll be going to TechCon.
Yes, sir.
In October.
Yeah.
So if you're there around there, reach out.
Yep. It's in San Jose, in case you're wondering.
Yeah, true.
And then anything else? The voice road test.
Yeah, the voice road test. I think the submissions are still coming in.
Oh, okay.
There have been 3 so far that have been really great. Go check them out. Great reviews, great projects as well. Super excited about those. We'll put the links in the description.
Mm-hmm. Yep.
Yeah.
And this past weekend, we went to a local hackathon, Shell Hacks. It's a MLH, Major League Hacking sponsored hackathon. There were, supposed to be like 1,000 people there?
Yeah.
It was a lot of people there.
Yeah.
And we had our own challenge. We put in a bunch of hardware kits into the hardware lab, and then we had some people create some really cool stuff, like a steering wheel that would vibrate if it was using CV to see if your eyes were closed, and then it would vibrate the steering wheel.
And then also have Google Assistant start a conversation with you. So
to
cool.
wake you up.
Yeah.
What did the winning team do?
The winning team did. It was called Care++. It was basically a device that would be on say an old person at an old home, and it would have fall detection on it and immediately call someone if you fell. Also just environment monitoring, so temperature, humidity, pressure, things like that, as well as an NFC tap feature where it would load your medical history for when you visit the doctor's office.
Yeah.
So it was pretty cool. They 3D printed these nice cases for the creator, and it was just very well presented. We'll post some pictures and videos on social media on Thursday for a throwback. And then we also had another project which was really cool that they didn't end up winning, but they did a smart shopping cart where you like tap like with NFC, and then they authenticate you via like a picture, and then also they take pictures of the different like things you bought, items you bought, and it's all happening on the Azure cloud. And they're using the Azure like machine learning like neural network that's already there to like do the comparison and mapping and things like that. So that was also really cool.
It was a lot of fun projects. We were there all 3 days, so a little tiring, but it was fun. It was great to see people working on the devices.
Yeah. People had a lot of fun, and like if you aren't familiar with Matrix Lite, check it out because that was a hit for the hackathon. A really easy coding in JavaScript, Python, or Golang. So all right, I think that's all.
Cool. That's it. Well, thank you guys for watching, and we'll see you next time.
Bye.